All right, we were going to wait until the end of the century so I could actually validate the projections I'll be talking about, but that was Claudia's joke, so thanks for that one. I'm going to lead off this morning to share a few snippets of the climate science research that we've achieved over the past 6 years through REACCH. REACCH was not really a climate change research project. There was a subset of the REACCH project to look at climate science, and so I'll talk a little bit about that. And of course, that's important because it feeds into a lot of the other impact work that we've done that really also impacts a lot of the decisions that are made across the region. I don't have a way to advance slides. I need to actually hit this, don't I? There we go. Okay, so as we know, the right combination of energy and moisture enables us to cultivate crops in various geographic regions across the world, including the ability to cultivate dry land wheat in the Columbia Basin. And the geography of climate across the Northwest shows these tremendous gradients in energy and moisture, and those gradients end up helping to determine where we can successfully cultivate dry land wheat and the subsequent yields of wheat. And so big picture, fundamental to the climate science and the impacts of REACCH is getting the idea of how the tapestry of energy and moisture are expected to change over the course of the 21st century. Because ultimately this impacts everything from future crop yields to pest interactions to regional economics. Okay, I wanted to highlight 4 impacts that we've had achieved through REACCH in the broader field of climate science. And first is the question of trying to understand reasons for changes in climate across the Northwest. And we know that there have been a number of studies that have looked at trying to understand sources of changes on global timescales, at global scales. We wanted to understand how this is played out at regional timescales and seasonal timescales. And Sanford showed you actually a figure like this earlier. And if you look closely at that figure, one of the interesting things that showed up in it was that in springtime, since the 1980s to present, temperatures across the Northwest in spring have actually cooled a little bit. It's a bit confounding, right? At longer time scales, at annual time scales, we see warming, strong warming across the region. And in the study that we published in the Journal of Climate, we were able to attribute changes in climate for the Northwest at seasonal timescales. And what we found in general was that man-made climate change, anthropogenic climate change, was the dominant driver of long-term changes, mainly warming. But that natural variability, things like El Nino, the Pacific North American pattern, can at times either compound or oppose the long-term warming trends. The second impact that I'll mention is that in order to get some information about the future climate for the Northwest, we have to rely on models. As Earth system scientists, we cannot conduct lab experiments on the planet. We have to rely on numerical models of how the Earth system works and the climate system. And it turns out that there are a number of modeling agencies across the world that run complex climate models. One way is to just use all the models blindly in a democratic system. What we did instead was we came up with a method for evaluating the credibility of how well these models simulate regional climate, specifically for the Northwest. And the idea behind that is we wanted to choose models that simulate climate decently over the contemporary period and then use those models as a basis for having our projections moving forward. So we came up with an objective method of doing this, and it's a complicated sort of carpet-type diagram here. The bottom line is that this method has been used for decision-making in terms of choosing models in various regions across the United States and across the globe. Third impact that I'll highlight, we produced a lot of data. You'll hear more about that throughout the day today. Fundamental to the REACCH project was to provide some climate data that could be fed into the crop system modeling you'll be hearing about more later, and that of course feeds into some of the economic models that you'll also hear more about. We developed 2 fundamental data sets. One is a real-time historical gridded weather data set that covers the continental United States, updated every day. That's used in a sort of a decision-making context. The other data set we developed was basically an approach for taking coarse resolution climate model output and translating it down to local scale so that could be used by a lot of the models that we are sort of using here today. And the method that we used is something called the multivariate adaptive constructed analog. You might hear that referred to as MACA later on. And that's a data set, an approach for not only getting information on temperature and precipitation, but also things like wind, solar radiation, humidity. Basically, all the variables you would need to run a crop system model, an ecological model, a hydrologic model. These data sets have actually, were actually not just performed for the REACCH study area, they were performed for the entire United States. The impact of that is that these products that we produce through REACCH, the science we produce through REACCH, is being used by researchers and decision makers across the United States. The pine cap across the southeast is basically using the data sets that we've developed. We've also updated some of the regional projections for the Northwest in terms of climate change, and I'll just touch on those briefly because they might feed into some of the things you'll hear more about later on today. The models, by and large, project substantial warming over the rest of the 21st century. We've seen on the order of about a degree and a half Celsius of warming to date since the Industrial Revolution. We expect that to continue. Basically, all models suggest warming. By the mid-21st century, our sort of target timeline, we're expecting an additional 1 to 2 degrees Celsius worth of warming. Precipitation is more uncertain. The models, by and large, are tending towards a slight increase in precipitation, nothing to get extremely excited about, but it does actually factor into some of the impacts from a crop yield perspective. Basically, a little bit more precipitation in the wintertime, a little bit less in the summertime. So for winter cropping systems, that can actually make a difference. And then I'll highlight the fourth impact. We've been doing a lot of work with climate data, and we've also been thinking about how to use this climate data in the context of agriculture, and specifically how climate change might influence the geography, the changing geographies of where we can cultivate crops. So while the REACCH project is specifically focusing on wheat systems in the Columbia Basin, my PhD student, Lauren Parker, who will be defending next month, she's been looking at changes in where crops can be cultivated in a changing climate and where crops that are currently grown may not be successfully cultivated. This is one of her studies from last year showing changes in cold hardiness zones. One of the things that we find is that the coldest day of the winter actually warms at a substantially greater rate than the average winter temperatures. Wanted to briefly mention future directions. Climate science continues. We're going to keep trying to solve this problem. This is basically the state of climate science and most sciences today. We know quite a bit. We are filling in pieces of the puzzle. The puzzle will never completely be solved. The big picture is pretty clear. And so regardless of whatever else is going on, as scientists, we will continue filling in these pieces to the puzzle. We are doing some continuing work looking at the changing geography of specialty crops. My grad student, Lauren Parker, is looking at whether or not almonds, which are primarily grown in California, a huge cash crop in California, whether under a changing climate, there may be opportunities for novel regions for almonds in the Northwest. And I'll briefly just close by mentioning the contributions of the climate team. There was myself at the University of Idaho, a number of grad students, Catherine Hegovich, who's a postdoc, and then Philip Mote at Oregon State University, his PhD student, Shihan Lee, who's here today. They did a lot of interesting work that I mentioned, as well as looking at regional climate modeling experiments. And we produced a number of peer-reviewed publications. We have actually had a fairly substantial impact to date. And we've produced a lot of climate data, and that data set there is just what's being archived here at the University of Idaho. There's a lot of data that has been produced by the regional climate prediction.net experiment as well. So with that, I'll end.